Alright guys, so in this video we're going to look at non-rigid transformations. And with non-rigid transformations, really what we're going to see are stretches and shrinks, both horizontally and vertically, from our function, from the graph of our function, right? First we're going to look at horizontal stretches and shrinks. And this is sort of the more complicated of the two scenarios. In general, we're going to sort of tackle it in a very similar way to the way that we looked at horizontal shifts. So right here, I'm going to look at one ordered pair and then think about what I would have to do to the x values to give me that same function value. So right here, in general, we're going to say that a horizontal stretch happens when we multiply by a number less than 1 inside the function, right? So right here, we've got f of x equals 3x minus x cubed, right? And what we're saying is that if we multiply by f of x equals 1/2 x, which would be 3 times 1/2 x minus 1/2 x cubed, that we would see a horizontal stretch from the function, right? The function would stretch horizontally. Now, in general, right here, what I'm going to do is just plug in an x value. I'm going to say x equals 1. We're going to look at the x value of 1, and we're going to say that when we plug in 1, we've got f of 1 as 3 times 1, and then minus our 1 cubed, which gives us f of 1 as 2. And that gives us, of course, the ordered pair right here. That is the local max. It is 1, 2. So I'm going to sort of erase some of this so we've got a little bit more space to work. So with f of 1 as 2, we've got that ordered pair, that local max. And now what I'm going to say is, in a sense, what I had to do to get that local max of 2 is plug in the x value of 1. F itself, which is 3 times an input minus that input cubed, had to evaluate 1 in order to get that max value, right? And essentially right here what we would say is, what in this case does x have to equal in order for f to evaluate 1, where it will give us that local max. And right here, if we think about the x value that we would have to plug into 1/2 times x, that would of course be the x value of 2. So right here, when we plug in 2, we get f of 1/2 times 2 equals 3 times 1/2 times 2 minus that 1/2 times 2 cubed. And of course, right here, this is f of 1, which gives us 3 times 1 minus that 1 cubed, which is 2, right? So in a sense right here, what we're seeing is the x value of 2 now give us that max of 2. So right here, moving into the ordered pair that we've got, well, so sort of reapply that max right there. And we can now see that we're seeing that max, instead of happen at the x value of 1, it happens at 2. And in general right here, we would have to say something similar to all of the x values that we plug into f of 1/2 x, which is they have to be, the x values have to be 2 times what they were for f of x in order for f of 1/2 x to process those same x values and give us the same function values. In a sense, what we'd see is a graph that looks something like this. Now, if we think about this more broadly, really what we're saying is all of the x values that we plugged in are slowed down by the fact that they're multiplied by that 1/2, right? So what we're really seeing is that it's taking longer on the x-axis for us to get to the same function values, because immediately when we plug in an x value, it's multiplied by 1/2, and it is basically evaluated as half its previous value. When we plug in 2, right, it's evaluated as though it's 1. It takes us to get all the way out to 2 before we can get to that max that we saw at 1 for just f of x. So right here, looking at horizontal shrinks, it's that same philosophy, and now what we're saying is that when we multiply by a number greater than 1 inside the function, we're going to see a horizontal shrink. And essentially right here, we're seeing an increase in the rate of function values. We can look at this the exact same way. We know that when we plug in 1, I'm going to do this on the other side. We know that when we plug in 1 to our f, we get the output of 2. And right here, if we plug in 1, or I'm sorry, if we looked at plugging in an x value, so that f would evaluate 1, we would have to say that that would be the x value of 1/2, because right here we would have to plug in 1/2 right there in order for 2 to multiply 1/2 and give us 1 for f to evaluate to give us that local max of 2. So right here we're actually seeing that same function value of 2 now happen at the x value of 1/2, and we get a graph that looks something like this. Now again right here, it's that same philosophy. Essentially what we're seeing is our function sped up, right? All the x values are twice their value when we plug them in, right? So essentially what we're seeing happen is the function happen much quicker on the x-axis, right? We reach x values much quicker when we're multiplying every x value by 2, right? We're doubling every x value. We're evaluating the double of every x value, so all the function values happen faster on the x-axis. All right, so that is horizontal stretches and shrinks. More complicated than vertical stretches and shrinks. Vertical stretches and shrinks are pretty intuitive. Right here, if we're looking at a vertical stretch, we would say that that happens when we multiply the function by a number greater than 1. And really what we're talking about is multiplying the equation of the function by a number greater than 1. So right here, if I take my f of x as 3x minus x cubed, just like we did before, I want to remember that right here, this equation is basically giving me my y values for the x values that I plug in, right? So essentially right here, when I multiply f by 3, or that equation by 3, really I'm multiplying all my y values by 3, and that's going to be a vertical stretch of 3. So right here, all of the y values defined by our equation are now multiplied by 3, right? And we basically get, let's say, that ordered pair of 1, 2, vertically stretched all the way up to 6. So right here we're seeing the function value of 6 at the x value of 1, right? This sort of goes back to what we talked about at the very beginning, right? Essentially right here we're seeing the function values themselves change when we do something to the outside of the function. And when we did something to the inside of the function, we had the same function values, but they happened either much sooner on the x-axis with a multiplication greater than 1 inside the function, or much later on the x-axis with a multiplication less than 1 inside the function. Right here, when we multiply our function by 1/2, again, remember that the equation of the function gives us the y value, and if we multiply the equation of the function by 1/2, we're essentially multiplying the y values by 1/2, and of course that's going to shrink the function values down to 1/2 their previous value, and we get a horizontal shrink. And we get a graph that looks something like that. Now obviously these graphs are perfect. You guys can type this into the calculator and probably see a better picture, but that's the idea of what we're seeing here, is that basically we're multiplying the equation that defines the y values by 1/2, and that gives us y values that are half of their previous value, or function values that are half of their previous value. Okay, so what we're going to do now is evaluate transformations. I'm going to do one, and then we'll have you guys look at one. In general, right here, it's the same philosophy we had before when we talked about multiplication directly to x inside the function. Previously, we saw a negative on the x inside the function, and with our example right here, with our g of x, we're seeing a multiplication of 3. Now, if we take a look at this in terms of transformations, what we want to recognize is that we're really not going to be shifting 12. We're really going to be shifting, when we factor that 3 off of the inside of the function, 4 units to the left, right? So in general right here, what we want to think is whenever there's a lead coefficient on the x inside the function, in this case the function is the square, whenever we see a coefficient other than 1 to the x inside the function, we want to factor that off of the inside of the function, keeping that 3 on the inside of the function because it's still going to be a horizontal shrink. But right here, what we want to do is keep that inside the function and then evaluate the transformations from x out. So the first transformation we're seeing is left 4, from the addition of 4. Then we can talk about the multiplication of 3, which is inside the square, and that's going to be a horizontal shrink. We'd say by, and here's where it's interesting. We're not going to say it's a horizontal shrink by 3. We're going to say it's a horizontal shrink by 1/3, right? Because we are 1/3 of our previous width, right? So a shrink wouldn't be by a factor of 3. A shrink would be by a factor of 1/3. Now, finally, we can talk about operations happening outside the function, and basically we just have that negative, which is going to be a vertical flexion over the x-axis. So right here, evaluating all these transformations, some of them we're going to have to be approximate with. Whenever we've got a horizontal shrink, it's a little bit tricky. But right here, we'll first take our graph, and we're moving this guy left 4, so we would go left 4 with our graph. And now right here, just like the reflection, we want to think that that horizontal shrink is happening around where the function thinks 0. So right here, basically what we would say is we're going to be 1/3 the width, but we're shrinking around x equals negative. So right here, we would basically get thinner around that, and I'm going to sort of try to draw this accurately, which is not going to be easy. 3, 6, 9, and so right here, I mean, 3 out, and there we go. So that's going to be approximately the shrink. This you would see more on the calculator. And now finally, we're going to see the graph of this guy vertically flipped, so flipped upside down. And that's a flip over, oh, come on. All right, we'll just try. Oh, there it is. Interesting. And that's a flip over the x-axis, right? So that would be this transformation, this graphing this g of x with its transformations. What I'm going to have you guys take a look at next is this one right here. And essentially right here, what you want to do is go ahead and remember that when we've got a lead coefficient other than 1 on x inside the function, we have to factor to see the transformations inside the function. So why don't we pause the video here, and you guys can give this one a shot. All right, guys, so let's take a look. Here we're listing the transformations first. So right here we would say, after we factor that negative off the inside, we can see that we're moving left 4. And then we have the negative on the inside of the cube, which means a horizontal flip at x equals negative 4. And then we've got the vertical stretch by 2, right? And again, we're seeing y values that are twice as large as they were before when we multiply by 2. And then finally, with the addition of 1, we're moving up 1. So let's see if we can make all of those transformations happen. Right here, first we're moving left 4, so we go left 4. And now right here, we're seeing a horizontal flip at x equals negative 4. So I'm going to highlight that and flip him left to right horizontally, which is the graph we're seeing there. And then right here, we are looking at the vertical stretch of 2. Now, you guys might think that this is going to be really tricky, but essentially, if we can evaluate, if we can sort of see some ordered pairs on the cube, which we know some ordered pairs, right here we can say that if we look at the ordered pairs of the cube, we have 1, 1, which is correlating to this ordered pair, which is negative 5, 1, and we have negative 1, negative 1, which is correlating to this ordered pair right here, which is negative 3, negative 1. And right here, what we're saying is those y values are going to be doubled. So right here, instead of 1, we're seeing it at 2, and we can say that we're seeing this guy at 2, and we can sort of get an idea about what that stretch is going to look like. It'll be a little bit thinner, like this, coming down. I mean, if you have questions, it's always a good idea to type it into the calculator. And next, what we're saying is this graph is going to be moved up 1, so we move this graph up 1, and that would approximately, I'm going to take this guy out, that would approximately be the graph of our transformed function. Now, in general, giving you guys stretches or shrinks, both horizontally and vertically, would be tough to graph freehand. So that would be something that we would probably need to do some work around. But you can go through and identify those transformations just by writing down what they'd be. So what I want you guys to do is to go through and take a look at all of these and identify the transformations that we're seeing going from our first graph to our second graph. So for example, right here, I'm looking at y equals x squared for my first equation, right? I have these transformations to look at for my second equation, and I can say they would be left 3 from the addition of 3 inside my square, and then right here with that multiplication of 2/3, I can say that would be a vertical shrink by 2/3. And so those would be all my transformations that I'm seeing for A. So why don't you guys go ahead and try the rest of these, and we'll come back and take a look at them in a second. All right, guys, so right here, looking at this first one, there's nothing else to really factor that negative 0.5 away from on the inside of the function. So really, first what I would say is we're seeing a horizontal flip at x equals 0, since there's no horizontal shift that we're seeing. And we would see a horizontal stretch by 2, which is, of course, the reciprocal of 0.5. So 0.5 is, of course, 1/2, and the reciprocal of that would be 2, and that's what we're seeing that horizontal stretch by. Looking at the rest of these guys, we can take a look at C. Here we are going to factor 2 off of the inside of our function and see that our first transformation is going to be 2 to the right, and then we've got a horizontal shrink by the reciprocal of 2, which would be 1/2. And then right here we're moving down 3 for C. With D, we want to factor the negative off of the inside of the function, and we'll see then that we are moving right 6 with a horizontal reflection, or flip we could say it both ways, at x equals 6. And then right here we have a vertical stretch by 4, and after that we're taking all those function values and moving up 7 with them on the y. Finally, this last one is tough, and there are a couple different ways to look at it. I'm going to show you the way I did it. So basically what I said is I want to create the transformations I'm seeing right here on this with this equation, and then I want to see what I had to do to compensate for those transformations. So the first thing I said was, if I take x and make it x minus 2, then I would have to add 5 to get my 3. So that tells me that I'm moving left 5. And then right here outside my square, if I introduce a multiplication of 2, I've also got to introduce a multiplication of 1/2 to get that basically 1 out there. So right here we would say that's a vertical shrink by 1/2 from the vertical stretch of 2, right? So right here I want to take a look at one more kind of problem, rather, and we will then call it. So right here, in this problem, basically we're given I'm going to cut it right here.